Okay.
All right, welcome everybody to the next installment of our Quantum BC seminar series. So today we have Lukas Chrostowski. He is a professor of electrical and computer engineering here at UBC. And he's also the program director for our Insert Create in Quantum Computing, and he co-leads the Quantum Silicon Photonics Design Fabricate Test Workshop. And Lukas is going to tell us today about hardware.
Excellent. Thank you, Olivia. Thank you to all the audience. Thank you for the invitation to be here. We have a very diverse audience here, from quantum experts to never heard of quantum. So I'm going to, I guess, hopefully there'll be some elements of that tickle fancies for everyone here. So this picture, maybe I'll introduce a little bit. This is this picture of this little boat is actually where I spend a lot of my time on. So in June, when I was away for a couple of weeks, I was sailing around Vancouver Island in this boat. So we just kind of threw it into the logo because it captures a lot of things that I like about British Columbia, like the snowy mountains and the sunshine and the oceans and all that. So, okay, so my discussion, my topic is silicon quantum photonics. And so you'll see, I'll give little introductions to those three words and how they all tie in together into this field. So a little bit of motivation for quantum computing, quantum BC. I think that'll be a rather quick one. Many of you probably have never heard of silicon photonics, so I'll introduce that in quite a bit, and then I'll go into the combination of how silicon and photonics meets to do quantum computing and other activities. And so I'll talk about how we fabricate chips, how we do testing, room temperature, and cryogenics, and describe some of the components, the units that are required to build quantum systems, and how to do, I guess packaging is also related to testing. So how do we do kind of long-term testing, at cryogenic especially? Okay, so briefly getting into the motivation for quantum computing. Computers are reaching their limits in terms of 0 and 1 computation, and quantum mechanics has these new properties that add to it, which is two main things, which is superposition and entanglement, are things that are not available in classical computers. And so there's a potential for these computers to solve some interesting problems. And I guess the ones that are, I think, most easy to understand and maybe the most promising are the ones that involve some sort of simulation of a natural system that is quantum mechanical underneath. Then you can imagine a controlled quantum system would be able to simulate a naturally occurring quantum system, such as solving nitrogen fixation as an example. So a lot of commercial activity in this area. This is just kind of a picture for those of you that haven't seen too many applications, but basically quantum computing aims to solve all the world's biggest unsolvable problems. So that's a pretty exciting direction. In terms of qubits, you've probably been seeing lots of discussion on spin qubits, and the ones that we're going to be talking about today are photonic qubits, and we're also going to be doing photonic and spin qubits. And so the general concept is 0 and 1, or superposition thereof. And in the case of photons, you can think of defining a photon as having a polarization. So horizontally polarized light, vertically polarized light, just like in my polarizing sunglasses. But you can actually decompose light into many, what do you call those? Basis vectors. You could use circular polarization. So there's quite a few others, and you can describe it by this Poincare sphere that describes the kind of nature of the light. And of course, it can be in a superposition. So what's kind of neat about this is that if you take two diagonally polarized beams, and you add those together, that turns into circularly polarized. And the same things kind of happen with other qubits. That if you have, one state can be projected onto different bases. So the same kind of stuff happens in photonics. Entanglement is a kind of a neat phenomena of sharing this mutual information between multiple particles, and measuring a qubit allows you to extract information from it. So all this stuff started from Einstein and company looking at entanglement, and then there's, I guess the experimental demonstrations are really relatively recent, to the point where I'm putting up this slide, which is a Nobel Prize in 2022 of the demonstration of quantum entanglement. So yeah, still relatively recent. People are just starting to acknowledge the details of things that are going on in there. Quantum advantage is an interesting concept. Some people, I guess people have been calling it quantum supremacy. And basically the status of the field is there are now 3 groups that have demonstrated something that a classical computer cannot calculate. It's not necessarily a meaningful calculation, but it's still something that a quantum computer could spit out that a classical computer could not. And what's interesting to me about that is that with all the excitement about Google and IBM and all that kind of stuff, superconducting qubits, there's only one demonstration so far of that, whereas 2 of the demonstrations are photonic based, which is sort of this underdog in this whole race. And the first one is in China. You can see a picture on the left of like typical optical table setup, like really complicated experiments. And Xanadu in Toronto is doing a fiber-based, which still looks complicated, but it's plugging in fibers and delay lines and things like that. So it's a little bit more manageable kind of experiments. So where my interest lies is these kind of large-scale experiments. Can you shrink those down into a chip-scale activity and use silicon? And so the combination of quantum and silicon and photonics on a chip is where my interest lies here. This slide is sort of meant to maybe criticize all the other techniques, or at least maybe point out sort of where the statuses are. And so let's see, a few things I can point out. One is spin qubits are quite interesting. So that one there hasn't been as much attention. If you look at superconducting ion trap, kind of those are the main ones that people talk about. And spin ones are a little bit of a up-and-comer as well. So Chrostowski's group at UBC works on those hole-based, and Steph Simmons at SFU has been working on silicon ones. And then I guess, the question is, what role does photonics play in this thing? So I'm going to talk about kind of a few categories of where photonics can help in terms of quantum computing in this talk. But first, I'm going to pause and just say quantum BC, since we're here for the seminar series. So in British Columbia, we have a long history of quantum computing activities. The first hardware startup company, D-Wave, started more than 20 years ago, and the first software company in Vancouver here started 10 years ago. And since then, there's been lots of activities, including a project that I'm part of here, which is the CFI funded with SFU, called Quantum Leap, Tools for Universal Quantum Computers. So this is all about using silicon and quantum photonics, and this CFI led to the formation of Steph's company, Photonic, which is steadily growing these days. So, okay, so maybe I'll skip a little bit about this, because I think most people kind of already pretty aware of what quantum BC is about for this audience. So, so let me just skip that all along. One is, I will say, in terms of hardware, so my interest in quantum BC on the technical side is really on the hardware side. And so one workshop that I've been keen to help motivate the organization for was the superconducting workshop. So this happened now 3 times, and the last one was just last week, so 2 weeks ago. So students were in Quebec City learning how to design superconducting chips. And the workshop that I was involved in organizing took place in February. We'll probably do it again, I imagine, hopefully this year again. So this was basically a workshop on how to design silicon chips, not quite as complicated as some of the things that I'm going to be talking about in the talk today, but starting to get into the sort of the early seeds of what you can build with silicon photonic chips. And part of this was interesting. We had Xanadu give a couple talks, and there's a lot of overlap between what we teach in the workshop and what Xanadu is actually commercially implementing. So it's pretty exciting. We also have fabrication capabilities. So we have Applied Nanotools is a very low volume academic style foundry in Canada that manufactures this. They're in Alberta and UBC. So they use some of the UBC equipment, and we also do our in-house fabrication as well. Okay, so introduction to silicon photonics. So the electronics industry is partly where silicon photonics comes from. So the kind of the theory concept was maybe 20, 25 years ago, people said, the electronics industry is spending these billions and billions of dollars on the R&D just to develop new tools and processes and capabilities. And the photonics industry is probably at the time was easily a couple orders of magnitude smaller than even the R&D expenditure. So probably in total 3-4 orders of magnitude smaller. So photonics is used for the internet. I was thinking like your internet wouldn't work without photonics, but it's still relatively small compared to the CMOS industry. And what the silicon industry has really done is perfecting the fabrication, the materials, all the design methodologies and tools. And if we can leverage some of that to do optical systems, that was kind of the excitement in the field. And so we talk about silicon photonics as being defined as either integrated optics or photonic integrated circuits. So just like integrated circuits in electronics, we have photonic integrated circuits. And there's also a direction which is try to, because we're using the same tools and techniques and materials, the hope is you can integrate electronics and photonics. Turns out that it's pretty expensive to develop a process that has both. But that said, probably the first very successful high volume product actually had both electronics and photonics on the chip. So for electronics people, it's really exciting because now you have extra components that you didn't have. You don't have just transistors, inductors, capacitors. You now have lasers, detectors, waveguides, long delay lines you can couple to the outside world very efficiently. And so, yeah, so this is a book that I put together a few years ago with actually the co-founder of that company that I mentioned that commercialized these kind of silicon systems. And so the early days of this field for the first 20 years was all about data transmission. That was really kind of the 99.9% of the market is in datacom applications. And nowadays people are looking for a variety of other applications now that this technology is available. Can we make quantum systems out of it as well? So this is a kind of a laundry list of lots of different applications enabled by silicon photonics, and the one that we care about here today is this little small slice called quantum information processing for secure communication and for quantum computing. And quantum sensing, I guess, could be in there as well. Okay, so a little bit about what silicon photonics is all about. So the heart of it is these little things that are illustrated here as yellow. These are optical waveguides. They basically typically you operate them in what's called a single mode condition, where there's only a single solution to the wave equation in the cross section. So if you're thinking about it from a Schrodinger kind of picture, is that you have a particle in a box. Here we have a photon in a box, and this photon can only live in this state. And this picture here represents an electric field intensity distribution profile. But if it's a single photon, you can think of it as the probability of finding the photon inside. And what's neat from the quantum perspective is that you have a 90% probability of finding the photon inside the waveguide, but you also have maybe a 10% probability of finding the photon on the outside. So this is exactly analogous to the particle in a box problem. So this is one application of silicon photonics. It's used for biosensors. This is something that we work on at UBC. There's companies that have actually commercialized this. Even during COVID, you can actually get a COVID test where you put your blood or saliva onto a silicon chip and you can measure things. And so we've done experiments like that at UBC as well. And essentially what you're measuring is a change of the effective material. So that, like in your Schrodinger equation, you have your potential function, essentially the bacteria, viruses, or antibodies attached to the waveguide, change the environment, change the eigenvalue or the effective index in our case, and then you can measure that through, in this case, it's a resonator, and by changing the resonance frequency, you can pick up what is in that environment. So that's how these kind of sensors work. So a lot of these concepts I'm describing are, here I'm very specific to the biosensor, but the same concepts apply to different fields, and also in quantum computing as well. Another area that we worked on is optical computing, which is a little different than quantum computing. This is basically doing classical computation, but using photons instead of electrons. So the concept here is, can we build an optical neural network in an optical circuit as opposed to an electrical circuit? And so this involved all the usual requirements for a neural network, which is the ability of transmitting information like broadcasting. And so that was this, that's this function right here. Then you need to be able to weight the information, multiplying by some amounts, and then finally add them up and then perform a nonlinear function, which is actually this modulation as well. So you can basically create these recurrent loops where you have, this is by the way, just one neuron. But if you have many neurons, all the neurons can talk to each other optically. So basically have light communicating across a chip and doing these broadcast kind of networks. So we've been doing some work on that for the last few years on building neural networks on a chip. And so these are classical, operating in maybe 10,000 photons. And when we get into the quantum world, you can do the same kind of circuits, but apply them to single photons. And so this is a different network. This is a what's called a Mach-Zehnder an interferometer network. So this also has interference, but it's a little bit more complicated. It's in the form of a ring resonator. But in general, the main thing in optics is that you can transmit both an amplitude and a phase, and you can perform additions, vector additions of all the signals optically. And so that's the real kind of computing power, is that you have this vector addition, which basically is you can implement any matrix with complex numbers in it. You can implement that optically. And then if you have data flowing through it, that data can flow through at the speed of light, and you have essentially instant matrix multiplications. So that's sort of the promise of both the quantum computing and the optical computing. Of course, there's a little bit more to it than that because you have to include the cost, the energy cost associated with the lasers, the detectors, the electronics. You have to pump through, tens of gigabits per second of data. But once it's in the optical domain, especially when it's flowing through its passive linear matrix, that stuff is all for free. And it turns out that the scaling behavior, this actually works quite well. It's actually, you actually get crossings for free in optics, whereas in electronics, you have to go over to avoid capacitance, but beams, optical beams don't interact. So you can have light just cross straight through each other and build these linear networks. So I'm just going to walk you through this picture because I think it's a useful illustration of what one version of a photonic quantum computer would look like. And my research areas are really not in the architecture, but really in the specific devices, like the kind of transistor equivalent level. So one is laser sources. So how do you make lasers? Sometimes they're pulsed lasers, sometimes they're continuous laser. This one shows a very short pulsed laser. The laser goes in, gets split through these little beam splitters, and then goes into this long waveguide. The waveguides are essentially, now there's nonlinearities that occur. So at high power levels, you have generation of multiple colors that come out of it. And those colors actually create photon pairs. So if a high intensity beam of light will actually generate pairs of photons that spit out synchronized. And these photons are essentially entangled. So you can create these entangled pairs of photons just by shining bright light on a piece of silicon and then seeing what comes out of it. So that's a really fundamental unit cell, is these individual entangled photons, and then you can split them off through this network and essentially take all the blue ones over here, all the red ones over here. The red ones would be used, typically you could trigger the system on it, and the blue ones, then you put them through this network and then perform all these calculations. And then you can do even more entanglement in there through the measurements. And there's also some projections, so you can, that block sphere that I showed at the beginning, you could perform rotations. Rotations are actually pretty fun. Basically, it's just a phase shift or some kind of mixing that you can do, and so you can project your photon onto whatever basis you want. And at the very end, you have single photon detectors that pick off individual things, so you can kind of separate and program whatever problem you're trying to solve. You can program it here and in the measurements as well. So all this is probabilistic. So you're basically hitting the system and then hoping that you generate these pairs of photons. Unfortunately, there's a lot of challenges here. So how do you get these photons to, there's a probability, very small probability here, and the probability of all of them clicking at the same time is almost zero. So you basically have to do post-selection where once in a while, you actually get a result, and most of the time you don't. But if you're going to try to scale this up to a big computer, you're going to need to have some sort of delay and buffers and ability of multiplexing sources. And so that's one of the big challenges is you can imagine 1,000 of these sources, and then you see what happens, and then you find the one that worked, and you try to multiplex them together. So there's a lot of interesting R&D going on in terms of all these kind of aspects of how you create thousands of photons that are synchronously arriving at the same time deterministically. So lots of big challenges. So the parts that we talk about here are how do you get light into the chip? So this is one challenge that we work on is you've got this laser. How do you even get it into the chip? So that's, we spend a lot of time kind of thinking about that and doing it efficiently. Then generating these things. So this is the device that we're working on, this little ring here. And then also filtering out this green laser pulse. So you have to get rid of it because you have a high power laser and then you have single photons. It's like the worst possible case you can imagine in terms of filtering application, super high powers and one photon. So making really good filters turns out to be a really good challenge for engineers like me. Then we need all these various switches and modulators, so ability to route light, and this is not as simple as a switch like a mechanical or an electrical switch, even like a transistor, because these all operate interferometrically. So there is no little thing that can just combine beams and simply. So you have to apply basically phase shifts. So all these switches work on the principle of applying a controlled phase. You need a perfect pi phase or 3 pi phase. And so how do you get that phase correctly, especially in the presence of crosstalk and other kind of issues in calibration? So we make lots of those. And then the other one is the single photon detectors. So these are based on superconducting materials. So there's a connection to the superconducting field here. And this is basically like extremely thin pieces of metal, superconducting metals deposited on top of the waveguides that we're talking about. And again, they kind of evanescently couple and absorb that light through the metal. Okay, so a little bit of pictures. These are, I guess these are all UBC pictures of the types of things that we do. This is a kind of a beam splitter. So I did mention that you can split the light in half. So this is actually physically what it looks like. And you can see there's no contact. So it's actually what you can think of a capacitive coupling, but it's really just the evanescent field leaking from one waveguide to another. So you remember how I mentioned there's 10% of the light is on the outside of the waveguide. That 10% on the outside will actually kind of get sucked into the other waveguide. And this is actually analogous to what happens if you take hydrogen and bring them close together, you get a hybridization of the wave function. So here what happens is the optical mode of the photon inside the waveguide starts off in one waveguide, and by the time it's in here, that photon exists simultaneously in both waveguides. And it's only when you measure it that you find out where the photon is. But before you measure it, the photon actually exists in both paths. So this is, I don't know, I find this super fascinating. It's really the heart of how all this computing works, and that, this principle applies to all the different qubits. But it's pretty interesting when you start thinking about ring resonators, and now you have light in the ring and outside the ring at the same time, and then you can imagine the light is in the circuit everywhere in the circuit at the same time. And only when you measure it with a single photon detector do you find out where it really went. Okay, so let's go back to how photonics and silicon photonics can fit into quantum computing. A little bit of a review of different approaches that people have been thinking about for computation. So the field really took off. Kind of KLM was a group of people from Waterloo figured out this idea and came up with a scheme for photonic-based computation. And there's different ways of encoding the information. So the first one is polarization. This Nobel Prize that I mentioned at the beginning of the talk, they demonstrated this entanglement using photons. And the idea is that the photons can be horizontal or vertical polarized. So that turns out to be a pretty convenient way of doing it. The other one, this is the one that the Waterloo group started working on, which is where you don't know where the photon is. So remember in this picture, I said you inject a photon here and it's going to be present in both waveguides at the same time. So you can now encode essentially a 0 or 1 where you don't know where the photon is. And so there's two different encodings. This one is the presence or absence of a photon, which is not the best way. And then this is the more popular way, turns out to be a bit more robust and easy, is you don't know where the photon is. So you always have a photon, but you don't know if it's in the up waveguide or the lower waveguide. And so with this kind of idea, you can have a superposition where you have 50-50 or any other combination. And of course, you have all the phase information as well. And so you can have relative phases between these different waveguides. So path-based entanglement. Actually, Bristol has the world's first online quantum computer. So you know how now IBM and all these other companies have that. Bristol actually put this up probably a good 10 years ago. There was actually like a 4-qubit processor that was running on this approach with photonics-based with waveguides. So that's pretty neat. And then a bunch of people from Bristol left and created PsiQuantum in the Bay Area that essentially is trying to build millions of qubits using this approach. So, but you don't hear very much about them. They're very secretive. The one we hear about a lot more is about Xanadu, which I don't really even have in here. So time is another way of doing unknowns in terms of where the qubit is. You can imagine having nanosecond or picosecond apart in terms of time, and then the uncertainty is where is the time. So that's an interesting one. And one that I got excited about a couple of years ago is frequency-based qubits, and we actually have a couple of, or 3 undergrad students actually working on that right now, is trying to do the qubit where you don't know what frequency the qubit is. So remember that light has a property of color, and if you don't know what color it is, that could be a qubit. So it's either a red or a green qubit in different frequencies. And it turns out that there are ways of changing the color of a photon, which, again, that might kind of sound crazy, but it turns out a photon has a carrier, let's say 200 terahertz. And if you apply a modulation to it by essentially wiggling electrons up and down in some kind of structure, that superimposes on top of that carriers onto the 200 terahertz. So you get 200 terahertz with carriers. And if you create a network of these modulators and filters and things like that, you can effectively build a switch that tells the photon to go from one frequency to another. So this topic has been, frequency conversion has been like a holy grail in photonics. Wouldn't it be great if we could build an optical network where you could switch colors? It's very inefficient, but for quantum computing, if you get a lot more out of it than just a switch, this could be an interesting way of doing it. So yeah, this is an interesting way of doing it. There's Oak Ridge National Lab was working on that for a while. So this is yet another way of encoding information. Okay, so let's see here. Lots of text. What am I going to say? So overview. I guess my message is all the approaches have major challenges. We really don't know what's going to succeed to 1 million qubits. It's a decade, 2 decades out from now, possibly, to get to error correction. And so I think photonics has to be part of the story somewhere. And I'll describe a little bit of differences. So one is photons don't have decoherence. So that's an interesting effect where people have observed photons coming from almost from the Big Bang or the other end of the galaxy, photons flying billions of years and still being coherent, which is neat. So they just really don't interact. The only way to get photons to interact is by having an electron present. And so fundamentally, all the processes that you can manipulate light have to have electrons, like glass has electrons in it, and that's what causes index of refraction. So pure flying, these are pure approaches where really photonics is the only thing that's doing the processing, is this flying qubit approach, so that the photons have to be moving in a waveguide or an optical fiber, and it's just different ways of encoding the information between Xanadu and PsiQuantum. The challenges are that photons don't interact, and so how do you implement nonlinearities if they don't interact? It seems kind of counterintuitive, but this is where this measurement-based approach comes in, where nothing happens in the middle of the circuit, it's really all at the end that happens. Okay, so what I mentioned is there's no decoherence, and they can travel across the galaxy, but anytime they travel in real materials that we can build, like a waveguide, there are electrons present in the systems, and you lose information when the photons disappear. And so we have this really big challenge where every photon counts, and we're losing photons like crazy. If you work out what is the decay time of a photon in a material, it's not hours or whatever. It's really nanosecond, kind of picosecond kind of timescales. And so yeah, just to give you an idea, in an optical fiber, we can go on the order of 5-10 kilometers before we lose half the light. And on a silicon chip, we can only go maybe 1 centimeter before losing half the light. So this is kind of a major challenge of chip scale things. So what we really would like is some kind of quantum memory. If you could get away, flying qubits are wonderful, but if you could somehow just catch them and pause, put them into something that lasts for a really long time, and then maybe take it back out again when you need to, that would be a really nice approach. So there's a variety of kind of schemes that people think about where it's like a hybrid computing system where you have photons and some storage, or you have a pure thing with storage, or really it's actually a superconducting system and you're using photons to interface to it with an optical fiber just to provide data. So, and then the idea is where silicon and integrated circuits come in is that eventually you'll need a chip scale solution to make a scalable millions and millions of qubits. So we're gonna have to figure out a way of how to do it on silicon, I think, and many people think as well. Okay, so photonics for quantum computing. One is the computation itself. So these are the 2 startups that you can go to right now. And now what is photonics really good for? It's really optical communications, right? So photons don't interact, they travel for a long time. And so how can you take advantage of these strengths of photonics? So one is to provide links between quantum processors. So if you think about superconducting qubits that will, you have 100 qubits in one fridge, another 100 qubits, can you provide optical fibers or other types to connect it? So that could be a role for that, and that could be quantum information. So you can imagine converting a microwave qubit into a photonic qubit, sending it over, and then switching it back into a microwave qubit or superconducting qubit. So that's one. IBM, I think, is maybe doing something like that, or at least I've seen they have some pipes between their things. Maybe they're not doing photonic-based, but some sort of photon-based anyway. The other one that's interesting is at the complete end of the spectrum is classical communications. So if you look at a D-Wave IBM fridge, there's 1,000 wires going into it or something like that. That's going to reach a limit. And so can we use optical fibers to provide information, communication capabilities in and out of the fridge? So with Joe and others at UBC, we're working on this MyTax-funded project to look at providing input-output into fridges. So that's a classical approach. And then the final one is this combination of quantum transduction. So this is really converting quantum information from that. So this is a pretty major field. It's got a long way to go before you can really get the one microwave photon to an optical photon with 100% efficiency. A lot of the numbers in the research papers are 10 to the minus 6, 10 to the minus 5. People get really excited when they jump up 10, one order of magnitude, but it's still really far away. But yeah, so there's ideas of coupling photons to various types of qubits, and each one of these, there's so many possible axes you could work on in terms of coupling one to another. And in some cases, people are even thinking about like a multi-hop thing, like going from photon to mechanical to superconducting. So there's a lot of ways people are trying to do this. And then the final one, which is, I'll talk a little bit about that, is the project with SFU, which is essentially combining spin qubits and photonic qubits at the same time, building an architecture for that. And there's a startup, Photonic Inc, that's pursuing that right now. Okay, so a few words about spin and photons interacting. So on this table showing these pure photonic qubits don't last very long, and that's kind of really the limiting factor. So it's not coherence in this case, it's just disappearing photons, as opposed to dephasing, like in the case of the other ones. The field that we're in terms of the spin photon coupling is actually called, is well known, is called cavity quantum electrodynamics. So some of those who are in the superconducting field are aware of C standing for circuit quantum electrodynamics. Very similar concepts. And this field started with nitrogen vacancies in diamond, which is a really difficult material to etch, as you can imagine. It's a hard material. Etching silicon is a lot easier, so the field is now looking at silicon. And silicon has lots of different types of defects that you can put inside it that can work as a spin qubit. And the one that we've been looking at UBC with SFU is this selenium, but there's a whole host of other ones that are out there as well. Okay, so I think this is the same picture already. Okay, so the way this architecture works is you have a single selenium atom. For those of you that want a more detailed version of this picture right here, Steph Simmons gave a talk at the Quantum BC workshop maybe 3 months ago, or at the seminar. So you can go back to her presentation. This whole proposal came from Steph Simmons, started in about 2017. Selenium was at the time thought to be maybe the best one in terms of really long lifetimes. There's really beautiful experiments. But basically the idea is that you've got this thing that has a really good memory for several seconds. And if you can do a dipole coupling to essentially the ground state and the excited state of the selenium atom, that's the optical, the photon comes along. So the light will interact with essentially the electrons, as I was saying, in the selenium atom. Okay, so electron interaction is key. So you've got a photon interacting with electrons. The electrons can jump energy levels, but there's also this splitting at the bottom, which is the actual qubit information. So that you're storing the information spin up and spin down in essentially the sort of the ground state of this electron, the 1s orbital, but you can also have the photon get bumped up to a higher energy level. So that's kind of the hybrid. And what we really care now about is strong interaction between the light and the matter. So one photon, one electron, how do you get them to interact? Well, the photon just flies by. There's like a 10 to the minus, super small number probability of interaction. But if you can get that photon to stay trapped and interact with it, like put it in a circle, put it in a loop, in this case, these are called photonic crystals. So what this is the light is forbidden to travel in any direction in this material. And so if there happens to be a photon where this purple dot is, which is this atom, that photon cannot go in any direction. So basically it just kind of stays present. So you're creating, just like that waveguide, I said the waveguide is this confinement in 2 dimensions, but it's still flying. Here we're trying to create 3-dimensional confinement where the photon just gets stuck inside there. And then that gives it just more time to interact with the electron. And eventually you'll get that interaction that you're looking for, unless the photon is absorbed, which is a problem. Okay, so a little bit more detail about these spin up and spin down. I guess maybe I'll leave it at this for now. But I'll just point out that there's a whole different types of materials being looked at. Selenium was the first. T-center is the one that Steph is mostly excited about these days. It has a wavelength that's compatible with all the data centers in the world. In terms of the wavelength is 1.3 microns, so it's really easy to get lasers and modulators and all the components are there. 2.9 is absurdly difficult to work with, and so there's just technical challenges there. But there's a lot, if you look at selenium, some of the properties are a little bit easier to work with in terms of, one of them that's not mentioned here is the number of different orientations that the T-center can have as well. But yeah, people are discovering lots of different other defects or materials that can be added to silicon. Okay, so this is where things get a little interesting and complicated from a circuit perspective. We had Giroux Yan, a PhD student from Jeff's group, working with Robert Rosendorf, and they basically said, how do we take this measurement-based approach that Robert was one of the inventors of and apply it to photonics-based system, like the stuff that's being worked on here? So the concept is you've got this 4-port device. It turns out you need a 4-port device to make these networks, and that turns out to be a major challenge. And depending on the status of the atom, maybe let's take a case where there is no atom first. So if you have no atom, this light can evanescently couple into this resonator, that forbidden region that I mentioned. And if it's on resonance, you'll see a little dip in the transmission. So what happens is the photon then gets coupled in, gets stuck in here for a long time, maybe it doesn't come out because it gets absorbed. And so that's what this blue dip represents. But if you have an atom inside here, and depending on the state of the atom, whether it's spin up or spin down, you'll actually get a modification of this response. So what you're creating here is this cavity QED, this hybridized mode between the photonic, the optical resonator, and the dipole transition of the atom. And depending on if the electron is there or in a different state, you'll get different responses. So this device can actually be used to read out whether the photon is in spin up or spin down state just by shining photons through it. And if the photon comes out here, it means that it was this orange curve, which is quantum state 1. And if it comes out of this other port, then you get this little blue spike, and it's in quantum state 2. So that's how you can do. So you have to have 2 detectors here, and you have your qubit in here. You send a single photon through, and you measure it and see what happens. If you didn't get it, if you didn't get a measurement, then you do it again. So you can do this determinate probabilistic. Now, I mentioned that measurement is the key to this whole thing. So before you measure it, you actually don't know where the qubit is. So it's possible that this qubit is in some sort of superposition state. And if you don't measure it, then things get even more interesting. You can actually cascade multiple of these qubits. So here you have this resonator coupled to an atom. You have the 2 output ports. If you measure it, well, you're done. You've destroyed the information. But if you don't measure it, then you take that information and you propagate it into a second qubit. And now you have this unknown state that's going into another qubit. Now what happens? Okay, well, it's some entanglement possibility. But it turns out that the only time you get entanglement for sure is if you happen to have measured a particular combination of clicks on these detectors. And then when you get that right measurement done, when that measurement occurs probabilistically, then you know that these 2 spins are entangled. So basically the entanglement operation is launch a single photon, wait to see what you detect. If you detect the right combination, which I forget if it's 1, 1, or I forget exactly what it is, then you know that they're entangled. If not, they're not entangled, or something else. So, so this is where it gets even more complicated with Robert Rosendorf's work, is creating cluster states and knitting and fusing and all these kind of operations that people get done. I guess what I was interested in is how on earth do you take a single resonator, couple them together? That was sort of step 1 of the question in this paper that we're trying to understand. But bigger than that, let's connect it to Robert's world of how can you take, how do you even create this fusion state? And so it turns out that you can create these little graphs, like physical graphs on a chip, that these successive operations will give you entanglement over many, many, many qubits, and you can create this whole sort of mesh of entangled qubits. And so, yeah, and then after that, you also have microwave control, so you can start applying operations. I guess I should mention the spin up and spin down is here. By applying microwave pulses, these pi pulses, you can do spin up and spin down, like rotations and arbitrary operations on the spin qubits. So it's basically using photonics to create an untangled web of qubits. So I guess the challenge is for me, this investigation is really helping me understand what I need to do for the next 20 years in terms of components. And fabricating chips is a hard part. I mentioned our loss numbers are terrible, like 1 centimeter is as far as we can go. So that's a major one. Cavities, we need to couple, just to show you the challenge here in this picture, we need a photon, a single photon that is resonant with the dipole transition of this atom. And not only that, but this photonic crystal has to be resonant. So we need 3 things on resonance: the photon, the atom, and the cavity of the resonator. And so adjusting the photon is maybe the easiest one, but adjusting the cavity to match the atom is incredibly difficult. And we also need to have this strong interaction, which is quantified by either cooperativity or I'll use this quality factor divided by volume ratio. So you need to have strong interaction at the right wavelength. So building these things is a big challenge. Single photon sources are a big challenge, and I think there's filtering I'm going to talk about today a little bit. I've highlighted just the ones that I plan to spend the last maybe 10 minutes talking about. Okay, so if you go back to this paper, the one with Jeff and Robert and company, we came up with this little ski hill diagram just to give you a sense of where the field is at. And you can see fault tolerance is a double black diamond. It's really far away from here. And so the question is, where are we on some of the green runs? And things like coupling, ensemble of emitters to a photonic structure. Okay, so there's multiple qubits in a resonator. For cell enhancement, this is where you have one atom coupled to a resonator. These are things that sound easy, but turns out actually quite difficult. So I'll give you a sense of where we are through a few examples. You see this picture come back up again. Okay, so fabrication. Silicon is manufactured worldwide by Taiwan, makes most of the chips in the world right now, but there's lots of others in the US and Europe and here in Canada. These are the kind of the research activities that we're doing. So the SiEPIC program is a research program involved which involves both training and chip fabrication in Canada. And we design, fabricate test chips, and we use lots of electron beam lithography and nanofabrication tools at UBC and other places around as well. Okay, so ideal of fabrication and design of these kind of structures. I'll come back to a few examples. Maybe it'll be illustrated a bit more. Once we've made the devices, testing them is a challenge. So we've made lots of these sort of room temperature apparatus. This is where you take your chip after it's fabricated and put it under an electrical probe station, but also we need to optically probe it. So we have in the background here's a laser, optical fibers, these little hair-sized pieces of glass that direct light into the chip, and we can perform these interference experiments that I was describing. Where things got challenging for this field was the wavelength. This is the first one, and then maybe I'll go through the 2 challenges. Wavelength and cryogenics, I guess, are the 2 big challenges. So I mentioned this dipole transition was at 2.9 microns, and there's basically nothing available at that wavelength. The optical fibers that you can get are made of this like zirconium stuff that you just breathe on and it breaks, super fragile. And there were no commercial lasers that you could get that meet the requirements for this application. So especially during COVID, it's really hard. We're building lasers and this kind of stuff, and it was kind of a challenge. But yeah, just building test equipment for working at this wavelength was difficult. These are some fabricated devices trying to get some measuring the quality factor, which is how long the light spends inside these resonators. So the higher the number, the better here. So these are the kind of things we fabricate. And then finally testing them at cryogenic temperatures. These spin qubits I didn't mention, they only work at cryogenic temperatures. So that's kind of an unfortunate part. Just if you look at the energy splittings between those 2 things, they're very small. We're talking about a few gigahertz kind of spacing, so you need to cool it down. And so how do you get optics into a refrigerator was not something that was too obvious how to do. And so we've been building a bunch of apparatus to do that. And so a few different ways. One is having mechanical, like this system right here that I showed actually has a mechanical alignment. So our first attempt was to put optomechanics inside the fridge to move the fibers around. So we got some early successes with that. And the other approach that we've been doing is making permanent bonds to optical fibers. So this is the work of Becky and Donald, working on a technique called photonic wire bonding, which is basically 3D printing a connection between the silicon waveguides and optical fibers that go off out of the fridge. And then this is a polymer that's being 3D printed, and you can design essentially kind of a waveguide that efficiently couples from one to another. So these are some examples of some of these resonators with those quality factors I was talking about. You can start seeing individual resonances on the silicon chip. And we can couple with reasonable efficiency. We're still losing photons, but it's not too bad. Okay, so cavities. So these are the resonators. The challenge here is the atomic transition that we're trying to couple to is about 100 megahertz in line width. And if you manufacture the cavity, remember we're talking about 200 terahertz is our wavelength, or 100 terahertz, somewhere in that range. The variation that we get in our manufacturing is on the order of 1 terahertz. So 1 terahertz divided by 100 megahertz is a lot. And so what it means is we really can't control our fabrication process anywhere close to what's required for this transition. So we can't do 10,000 times better. I mean, you can make 10,000 devices and hopefully one of them will work. That's a standard approach. But really what we're going to need is some tuning mechanisms. And, you know, unfortunately I mentioned anytime you have electrons in the picture that adds loss. And so we want to avoid electrons. And so we've been looking at different ways of doing it. Thermal optic, injecting electrons, those have problems. And so now we're looking at optomechanical systems, nano-optical mechanical systems, where we're making mechanical systems that we're moving things on a nanometer kind of scale. So this is a picture of what the device looks like. This is one of these resonators that's been cut in different places, and we're trying to move mechanically the silicon, and these gaps are on the order of 20, 30, 40, 50 nanometers. And by changing the gap, you can change the wavelength of the cavity. And if you had an atom in here, and if you had a photon in here, and if you could tune it, then you can get everything all lined up. So unfortunately, there's compromises here. The quality factor here is too low, and the mode volume is too large. So this structure won't work. And also, we have not been successful in getting it to really tune very well electrically at cryogenics as well. So this is kind of where we are with mechanical structures. We need a lot more work to fabricate these kind of things and test them. So I guess I would say number one of this keyhole was done. SFU has done this already. But number two, this is what I was describing, is what we're trying to do, and we're not there yet. And if you look at all the other things in here, we're really far from getting any of these. And gradually keep an eye on the results from a STEPS group from either the company or the university, and then you can assess to see where we are in the ski slope to see how we're progressing along. But I point out 21 is this dual rail spin dependent cavity waveguide thing where you have two of these coupled together. That's like really, really far away from here. So we're hoping to get to 1 qubit, and we're still not at 1 qubit right now, almost 5, 6, 7 years later. So. Okay, so here's what another group, this is from Denmark, this just came out fairly recently, I guess just last year, trying to push this quality factor divided by the volume ratio in order to confine the light, squeeze the light as small as possible to have it interact with the atom. And so this is like just some crazy exotic computer design structures that really try to maximize the electric field. Very heroic effort to fabricate this, and just to give you a sense of what people are trying to do outside of UBC. You can see this Q over V ratio in the 3 to 4 million. This is a student, Joshua at UBC, who's just graduated. So he's gotten this ratio up to in this kind of slightly higher than this other number, so 30 million. So this is a pretty interesting cavity where it's a one-dimensional cavity. Light comes in, bounces back and forth between these holes. These are actually mirrors. So the light is actually bouncing back and forth, but this little region in the middle here acts as like a little focusing material, and you can see the electric field is strongest right in that little gap. And so, the team at UBC has been able to make some really nice devices and get some really good performance out of these. But yeah, the wavelength of this is some random wavelength. It's not specific to a particular atom. So the next steps in this project would be to think about using this cavity with that atom that actually works at that red color. But this cavity is not tunable, so now we got to address the tunability. But in terms of the strong interaction, I think this is kind of getting there. Okay, next up is single photon sources. So this is, I guess we labeled this as a blue run on a quest. So for some of you who may have seen Raphael's presentation a couple months ago, he gave a demonstration of a quantum suitcase where he showed cool things, entanglement and Bell's violation. So just as a reminder, this was using a high power laser going into a crystal, spitting out different photons through this process. And we're using essentially the same, except instead of parametric down conversion, it's called spontaneous four-wave mixing. So related process, but again, the idea is that silicon is a crystal. You pump it like crazy, you inject lots of light into it, and then out comes, so you pump it at this wavelength and spit out. In this case, you get photons that are going in different directions. Here you get photons that are coming out at different frequencies, and but in the same waveguide. So, so the challenge with this is now you've got this super high power pump that's maybe 10 orders of magnitude brighter than the single photons. So you need a 100 dB filter that we need to design here. And so these are the kind of filters that we've been making at UBC, which are these periodic structures. And so you can see you have like maybe 1,000 of these little teeth. And by controlling the period and the shape and all that kind of stuff, you can engineer a filter of your desire. And so we've been making filters. You can see our filters here are maybe 50 dB. So we're maybe, I don't know if you want to call it halfway there, or maybe 1 million more to go, or whatever, but quite a ways to go. So halfway in dB, but a lot more to go. And so our actual experiments, and here's maybe this one a little bit better. Yeah, this is also another 50 dB. We've tried things like cascading these 50 dB filters, and we see that there's a limit. It just saturates, and we're getting basically photons bouncing around randomly in the chip. And so it's really difficult to make good filters. And so what we actually do in these experiments is you have the on-chip filter, but you also have external filters as well. So we'll do 50 dB here, 50 dB there. And then at the end, you can actually measure single photons coming out of the system. So one challenge we're working on is, can we just if we could do everything on chip, that would be wonderful. What Xanadu does and everybody else is external filters. Some on chip, some external. So then you have to quantify how good are these things. And so looking at how pure the photons are in terms of the photon relative to the dark counts, and then also how pure are they in terms of are they single photons, or are there two photons at the same time? So some experiments there. We have lots more to do as well. And Abdel is the student who's working on this. He's getting near the end of his PhD on that. So one of the challenges, like I said, is this scattering issue. Light just bounces around all over the chip. Okay, so the last topic is this coupling, 3D printing. So for those of you that are interested in fabrication and 3D printers are kind of everywhere, but this is probably the tool that can give you the smallest features in the world. You can get submicron blobs of this polymer material. And with this, you can basically make free-form optical structures. You can make polarizing beam splitters. You can make little beautiful lenses with periscopes on them, and lenses on top of detectors. And so we've been playing with essentially using this kind of tool that we purchased at UBC. We have a commercialization effort. So this is a company that I co-founded that actually offers this available if people want to get chips made with these little things printed on them. So you can get on the order of 50% coupling efficiency from a fiber to a chip. There are some additional challenges. 2.9 microns I mentioned. Turns out that there's OH absorption vibrational bonds, and so there's a pretty large, it's pretty opaque, this material at 2.9. So it's, I think we have doubts as to whether this transmission will allow us to make quantum systems at 2.9 microns with these polymers. So there might be some other material that could be used for that. So nevertheless, we're still using this for other things like how do you get lasers from, so you remember we need a laser source, high power lasers. So how do you get the laser into the chip in the first place? So this is what we're working on right now. These are 3D printed connections from the laser into the chip. And here's some recent pictures of some of the chips that we fabricate, lasers we attach, and some measurements. We can show that the lasers operate at a single color after all this integration. Yeah, this is a manufacturing process that we have defined at QBC. Okay, so conclusions. I guess I want to basically present to you a vision for the challenges for the field for job security for the next 20 years in terms of challenges. So one big one that's pretty universal for anybody that works on photonics is ultra low loss components. This was important for data communications, but for quantum systems where you really can't lose the photons, basically every component that we make can be engineered better and better. So we've gone from beam splitters that have a 0.3 dB insertion loss to 0.03, maybe 0.01. So we're kind of pushing those numbers down quite further. Active components, all these modulators, laser detectors, everything has to work at cryogenic temperatures and be lossless. So it's like massive challenges for the field. And then how do you control these systems? So I mentioned you have to control the phase optically. And how do you get electronics to work? Photonics is intrinsically an analog technology. It's not just like you can't just have switches, and so controlling phase is a really big problem. And so yes, that's an issue. Then we need, so these are all kind of classical challenges in a way. And then there's the quantum components, which are the detectors, the sources, the cavities, I guess you could say. And then eventually getting the atoms. I haven't even talked about how to get the atoms in the cavities. That's another challenge. And then the whole design, fabricate, test cycle. So being able to complete these experiments and finally put them into a system that works. So we think we have a way of doing it for O and C band, which are the telecom wavelengths. We still have work to do on the era. So yeah, so next steps. I guess this green run is really the next one we're on, which is this showing that we can make a cavity, showing we can get it at the right wavelength, showing that we can get an atom, getting all those three ingredients kind of talking together will be a pretty major milestone for this thing. Once this thing is done, I think it'll be pretty quick before you can start to get to 2, and then having 2 qubits will really be amazing, right? So right now the field hasn't even shown 1 qubit. And how do we get to 2 is another big order of magnitude. How do you get to 10,000 or a million or whatever is another story altogether. Lots of choices of materials, developing sources, detectors, so lots of work. Oh yeah, and then of course this gets even more exciting is all these measurements that you need to actually do quantum computing. Like this is, we're light years away from that, I guess you could say. So yeah, lots more work. So here's a vision that I guess I think photonics will go and quantum systems will go in the next few years is there's no single material that is perfect for everything, but we can use silicon as a platform for integration. So things like lasers, coupling lasers into these waveguides. Silicon is one material, but people are starting to look at lithium niobate, barium titanate, silicon nitride. There's lots of other materials that could be used to do the same functionality that we're talking about. And so here's an example of lithium niobate. Or maybe you want to do atomic systems like coupling to tweezer type situations. So I think integration is going to be a really important topic to scale these quantum systems, and I think optics is definitely going to play a role somewhere in there. And I'm looking forward to contributing towards this kind of fun technology. So with that, I'll say thank you. Thank you.
So many interesting, challenging things to work on. So are there any questions from either in the room or on Zoom? If it's on Zoom, you can just turn on your mic and ask away.
Go for it, in the room.
I was wondering, the device, I think it was on page 23. Is that like, that's just kind of like a very specific matrix multiplying device. So am I correct with that, or is it?
It's reconfigurable.
Okay.
So the question is, this is a specific matrix multiplier. So you have a limit in terms of how big the matrix is, but by controlling the little black things right here that have wires going into it are phase shifters.
Okay.
And so each one of these interferometers where you split the light in half and recombine it, if you have 2 control signals, you can essentially rotate the photon anywhere in the sphere.
Okay.
So imagine if you come in with a photon on the top, the output photon can be any linear combination of these 2 outputs.
Okay.
And so by making this mesh, you can create any unitary matrix by just controlling the knobs.
Okay.
So, but the challenge part of it is, yes, you can set it, but I think a lot of the early quantum supremacy experiments are like, well, we don't actually know what we put it in. We just applied a bunch of voltages, and then you measure it and you get some quantum experiment out of the output of it. But to actually do it like precisely, controllably, if you want to program a specific thing, you would need to know the phase of each of those things. And so that would require some sort of interrogation where either you calibrate it really well, or you send beams of light through and measure it kind of classically and say, like a very simple experiment is a high power laser or medium power laser. You can say, wow, 99% of the light comes out here, 0 comes out over here. Okay, good, I'm happy.
Okay.
So you'd have to kind of go through and initialize and configure everything to how you like it.
Any questions? I do have one, but I'll wait in case somebody on.
Anybody on the Zoom call want to ask a question?
Hey, Lucas, we have a question. All right, do we want to come? Yeah. Yeah.
Hi, Carl. Hi, SFU folks.
Yeah, Daria has a question.
Hi, Lucas.
Hi, Daria.
Question related to our graduate student education. How much cavity QED do you think people would need to know about to get the big picture of what's happening?
Sorry, how much? Sorry, can you repeat that? How much?
How much cavity QED should people know about ideally? Not everybody's
And
going
you
to.
said, and you said how much cavity QED, or is that what you said? The quantum electrodynamics?
Yep.
Well, that's a good question. There's two answers to that. If you really want to be a quantum person, you probably wouldn't want to know a lot. But if you're like me, then you can get away with almost none of it. So I think what's important is that the community, there's going to be a diversity. Like in the long term, there's going to be people who work on sort of the transistor equivalent, who have no idea how to build a system, but really know the physical details of the cavities or of the waveguides and things like that. And as long as there's enough communication from the upper layer where somebody understands the algorithm and the approach, like the Robert Rosendorf type people at and the theory. So I would say not everybody needs to understand it. I mean, I think the quantum field is so broad that you could sort of make everything required. But I think that's going to be really difficult. And so, but I think for somebody coming out of the quantum computing program, I think it'd be better if people knew more about cavity QED than I do. But again, there's probably lots of other topics involved in there. So I would maybe say that if you're covering circuit QED, it'd be useful to do cavity QED as well at the same time.
Okay,
And compare the two.
we'll make notes.
Okay.
Hi, Lucas, I have another question. So you mentioned that frequency encoding, does it limit the speed of the quantum computer because you need a very long pulse in order for the frequency to be resolved?
Let me just jump to that picture. Okay, so you want to know, does this limit the speed? This one right here, right? The frequency.
The right-hand side, yeah.
Well, okay, so I'll give you a general, rough idea of what are the frequencies that people are talking about, and you can see if that's a limiting factor. The numbers that people typically talk about are maybe 20 to 40 gigahertz splitting.
Oh, okay.
And the modulation is 20 to 40 gigahertz. So I haven't thought about it as a limiting factor, I guess. I don't know if that's a good answer.
Mm-hmm.
It's a pretty big split, and I guess there's two factors.
But the spectral light has to be very narrow, right? The red one and the green one.
Yeah, how narrow does it have to be? I guess it has to be narrow enough that you don't get sort of lead-ins, because this, at the end of the day, you're cascading these operations so that if you go through multiple stages, you don't want to have bleeding, and you also want to be able to filter them out. So that one of the constraints why people are picking fairly high frequencies like 20 or 40 gigahertz is because it's really difficult to make optical filters that have a sharp enough cutoff so that you can separate the green and the red. So I would say, I mean, this line with, just to give you a sense of a laser, well, I guess, yeah, you're right. If it's a pulse system, then it's an issue. Yeah, probably like a factor of 10 is enough, I would say, maybe 100.
Yeah, that would be fast enough, yeah.
So we're talking about, I guess, yeah, like sub-gigahertz line widths.
Yeah.
But I didn't mention, I was really excited about this field, but probably the biggest problem with this is when we talk about beam splitter, I mentioned, our best beam splitter that we made is a 0.01 dB insertion loss, which is like, I don't know what it works at, 99.99% splitting efficiency. This is effectively a beam splitter where you can come in with one tone and split into two, right? And the typical numbers are 3 dB, 4, 5, 6, 6 dB, maybe, excess loss. So your transmission through a fundamental unit cell in the system is only 25% for a beam splitter. So
it's classical. It's not even quantum anymore.
Yeah, so trying to build anything with this at this point, it's sort of like, I was like, oh my God. And so what's nice about this is that if we can, having this as a challenge for the photonics people, say, how can you make a modulator with 0.1 dB insertion loss of this thing? If you could do that, you can make billions of dollars in the telecom world. So I think there's some people who are kind of thinking about that, but there's definitely a lot of money to be made on every little component that we can make as a direct use for the data centers of the world and the cell phones and whatever else. But yeah, I think this one is a little bit more challenging. So yeah, we are working on a modulator that maybe will get us into the sub dB, but to be determined.
I have a comment about temperatures that you mentioned. So the fact that these spin qubits have gigahertz frequent energy differences is not the limitation on temperature, because you can simply take them like massively out of equilibrium with the environment. So the equilibration times can be very slow. So the temperature limitations come generally from other things. Like, for example, in the case of photonics, it's the detectors.
Okay, so I'm going to say no, but I don't know what the answer is. So I think the spin qubits themselves, well, unless you have a trick up your sleeve that I don't know, but I think the spin qubits themselves.
Let me give you an example. So NMR quantum computing works with gigahertz frequencies and was done at room temperature, right? So the problem is about initialization of the state, or like projective measurements.
But if you could put your detector outside, then so you're saying you could have a warmer qubit with external detectors?
Yeah, I mean, the qubit itself won't be warm because it will be massively out of equilibrium with its environment. So its temperature, effective temperature, will still be low, but the bath temperature could still be room temperature because it's just not that coupled to the bath.
Mm-hmm.
So the ultimate example of that is NMR quantum computing. They're really out of equilibrium with the bath. Of course, they can't initialize their states, so it's.
So I think some of the numbers, I don't think I have them in here, but I think there have been measurements of, I guess, these T2 lifetimes. Is that an important metric of what happens at higher?
Yeah, so like 1.5 Kelvin is like 120 microeV, and that's like way above the singlet triplet splitting, right?
Right. It's larger than the SSU.
Yeah, it's way bigger than that. So that's a mistake that quite common for people to think about, like that the qubit will be in equilibrium with the environment, but in fact, like a quantum computer is the most out of equilibrium system you can basically think of in quantum mechanics. Well, in experiments.
Mm-hmm. So do you think there's a prospect where this could be not in a fridge?
I mean, that's not what I'm saying.
Okay. It's just that the rationale for a cold is something different.
Yeah, it doesn't, like, you can take the system out. The only like time will tell if quantum computers how high of temperatures they can operate at becomes a question of devil in the details, right? Like how much is the electron phonon coupling, spin phonon coupling? It's like a question about like equilibration rates and stuff.
Okay, so is T2 the relevant metric that T2 gets worse at higher temperatures? That's important, right?
T1 and T2 measurement visibility. It's not just T1 and T2, because if you can't initialize it, then it's you don't know what state it's in. It doesn't matter if it has a long lifetime. It will still be in a mixed state. Its density matrix is mixed. Mm-hmm. So measurement fidelity is really important when the qubit environment is warm.
That's basically this whole thing, right?
Yep.
So if you have your detectors outside the fridge, detectors in the fridge, the qubit
out of the fridge. Yeah.
That's interesting. Well, that would certainly make things a little bit easier.
Yeah, I don't think, I mean, probably realistically, the fundamental reason or what would limit this is, probably free carriers at room temperature are gonna massively screw up the qubits. But, maybe 77 Kelvin or 20 Kelvin. And 20 Kelvin's pretty easy to work at.
Sounds warm.
Yeah, it's very warm.
Okay, in the interest of time, I think we'll take other questions offline, but thanks again, Lucas.
Yeah, thank you. Thanks
And,
for your time, everyone.
next seminar will be August, I don't remember the date, but that will be the 3 winners of our 3-minute thesis competition.
I'm looking forward to that as well. I think next week, is it next week?
Yeah, the competition's next week.
So we've got like 3 hours worth of 3-minute talks. That'll be really fun, and then we'll hear from the best ones, or the ones that are selected.
The ones that win.
The ones that win, yeah. Wonderful. Thanks, everyone.